Okay, so this is week 9. Today we're going to do combined loading. I'm going to continue on the example that we did last week. Okay, uh, in a sense of we're going to actually draw the Mohr circle already, and then we're going to talk about Mohr circle in 2D form. Okay, then if time permit, I'll go into shaft design theory. Okay, so just to remind you all that there'll be a quiz 6. It will be held on July 2nd. Okay, again, same time, 7 a.m. until 4 p.m., 1.5 hours. Okay, and there is no tutorial on July 1st because it's a holiday. Okay, so last week, where we finish off, I'm going to briefly look at last week's notes. Okay, where we finish off is we drew an element. Okay, so this is an element that we have drawn. Okay, and we realize that the element is under a normal stress load of 29.852 times 10 to the power 6, and then it has a negative shear configuration of 1.608 times 10 to the power 6. Okay, so at the end of the day, we have to select material for a structure that has been loaded like this. Okay, so we were doing on an example. Okay, so we were dealing with an example over here. Okay, I'm going to copy this example. Okay, so we are analyzing an example under the following loading condition. Okay, so this is our example. We will carry on, and we analyze the stresses. We broke down what are the axial load, what is a moment, okay, and what is a torque. Okay, we have done all those already, but for this case, there's no torque. Okay, then we look at element A. We analyze element A, and then we drew our element A. Okay, which I finished off. Okay, so we drew element A. So this is our element A. I'm going to copy the whole thing again. Okay, so this is our element A. So based on our configuration of our axis of our transformation, so we know that this is X, this is our Y, and the vertical one is our Z. Okay, so if I were to draw this element, okay, I will redraw this element. So this is X, this is Y, and then this is Z. Okay, so this entire element will have a load of 29. So let me draw up the element. This I think I drew two. Okay. So where we are looking at, we are working on element A. Okay, element A. Right. So we have a tensile of 29.852 times 10 to the power 6 Pascal. And then we have a negative shear configuration. Don't worry about positive or negative shear for now. Okay, I'm going to do 2D Mohr circle with you so you will understand better. And we're at 1.608 times 10 to the power 6 Pascal. Okay. So now we have looked at the stresses on this element. Okay. Then we're going to select a material for it. Okay, we're going to select material. So if we go to our material table, which I spoke about last week, and I'll do some recap. All right. So these are the properties of the material. Okay, these are the properties right? So as you look at the properties, right, we have things like ultimate strength, right? Then there's yield strength. Okay, you'll be saying, hey, why are we given both, right? So we spoke about this. You will use ultimate strength when you have brittle material, right? And then you will use yield strength when it's ductile material. Okay, so where we are analyzing this structure is a ductile structure, so we tend to use the yield strength. Okay, then we are given tension, right? Tension and compression. So these values you see over here, these values that I'm highlighting in blue now, they see over here. So this is under pure tension. Okay, then I'm going to highlight, and this is under compression. Now, which value will you use? Okay, because our structure has both tension, right, and shear, right? So where else these numbers that we have is what you see down here, okay, is unidirectional. Right, so when they do the test, as we recapped last week, they did it under pure. Okay, so this is just tension, right? And then this set of values over here also unidirectional. Uni means one, and for this case, in shear, they apply a torque. Okay, so this is just shear, right? But our structure, right, in reality, our structure is under both or element is under both tension and shear, right? Right, it's under tension and shear. Whereas when they did all these tests, right, when we were to draw their element, is either under tension or they do test, right, is under shear only, right? Whereas we have both. Okay, so the only way to link them, right, the only way to link them is to find the principal stresses of the element. Okay, so what the term that you here see down here is principal stress. So note, right, principal stress, or at the principal stresses in Mohr circle, right, the shearing stress is equal to 0. Okay, it's equal to 0. So we have to find the principal stress using Mohr circle. Okay, so what you see over here on a materials handbook, okay, this is in fact, okay, the tension over here is in fact a principal stress. And we see the shear. Okay, later on you'll realize this when we do 2D Mohr circle or 3D. This is your maximum shear. Okay, that is your maximum shear. Right. So we are going to do Mohr circle first. So I'm going to draw Mohr circle. Okay, some of you could remember, some of you that did 3CO3 with me will remember Mohr circle. Some of you could not remember. It's okay. I'm going to do all over again. Okay. So let's start constructing Mohr circle. Okay. So I'm gonna do draw a 3D Mohr circle. Okay. So because it's a 3D object or 3D stress view, I'm going to draw a 3D Mohr circle. Okay. So I'm going to label this first. Okay. So this is our point X. Okay. Surface is our point X. This surface over here is our point Y. And this surface is our point Z. So all these are relative to the transformation. Okay. So I'm going to copy this image again. So I'm going to draw a Mohr circle on the element to find the principal stress. Right. So in real life, we are going to deal with 3D Mohr circle, okay, because it's a 3D element. So over here, we know that stress Z is equal to 29.852 times 10 to the power 6 Pascal. We know that stress X is equal to 0. Okay. We also know that the shear, okay, shear on the IXZ direction is equal to shear in the ZX. Don't worry about all this XZ, ZX first. Okay, later on I'll teach you how to define them. Okay, so this is equal to minus 1.608 times 10 to the power 6 Pascal. And then we realize that stress Y on its own is also equal to 0 Pascal. So we're going to now construct a 3D Mohr circle. Okay, so let's draw the Mohr circle. I'm going to change it to a, yep, okay. So the vertical scale on Mohr circle is the shear. Okay, so this is our shearing stress. So I'm just going to draw. I'm going to start with 30. Right? Not 30. Maybe 16. 14. 12. Or maybe that's too much. I'll start with 20. Right? 20. 15. 10. 5. 0. So this is our shearing stress, minus 5, minus 10, minus 15, minus 20. Okay, and the shear is element rotation in a clockwise direction. Below is element rotation anti-clockwise direction. Don't worry about all this. I will go through this when I do Mohr circle. Okay, and then you have your normal stresses. Okay, so this is your normal stress. So you have minus 5 down here, 5, 10, 15, 20, 25, 30, and 35. So you have to make sure that the scale on the normal stress and the shear stress are the same. Okay, then you will get a circle, or not, you get an oval. Okay, right, let's see what we have now. So we know that stress X and stress Y are equal to 0, right? So this is your stress X and stress Y is equal to 0. Stress Z is equal to 29.852 So I'm just going to eyeball this. Okay. So this is approximately where your